Hi, my name is Stefano Marchidis. I work as Associate Professor in High Performance Computing at KTH, Royal Institute of Technology. So my expertise lays on high performance computing, but also been working on simulating magnetic reconnection in very different setup and developing tools for simulating magnetic reconnection. So this is the first lecture that I'm going to have about simulating magnetic reconnection with the particle in cell codes. I want to give you a brief outline of the lecture that we will need in order to perform the lab associated with this course. So in this lecture, I will focus on the first 3 points of this item. So what are peak simulations and what are the particle and particle cell methods, and which factor we need to take care when we are going to do simulation of plasma for magnetic reconnection. Particularly, we will see what the impact of particles, what is the impact of grid spacing and the time step. In the next lecture, I also then look at the more practical aspect of simulating magnetic reconnection. Particularly, we are going to look at one code called IPEAK3D. We're going to look at how to install, running, how to feed with the input file, and how to analyze the output. Together we will set it up, the code to do magnetic reconnection simulation, and then we will check. We will run the simulation and we will check what are the results, and we'll connect back to the theory. So the focus of this lecture now is actually about the concepts. I want you to understand the major concepts of peak simulation, and then in the next lecture, when we are looking at the more practical aspect, we need to remember about this important point. So the lab session will consist of using a tool called particle in cell simulation to simulate magnetic reconnection. So PEAK is a simulation tool to studying kinetic physics of a plasma. In its basic formulation, the particle in cell method has two major constraints. The first one is about the time step that we are using in simulation. This time step needs to be a fraction of the plasma period. So the plasma period is the basic time length in a plasma, and is the time that the electrons basically takes to restore the charge neutrality. So it's very fast, right? And is an electron quantity. We also have constraints regarding the grid spacing. The grid spacing, in order for the simulation to be accurate, need to be of the order of the bilength. So the bilength is again is a spatial quantity that is related again to the restoring the charge neutrality of a plasma, and it also is an electron quantity, because it's basically this electron motion that we want to have to restore charge neutrality at a very small scale. So because both these constraints, the one about the plasma period and the one about the bilength, are electrons phenomena, because of this constant, PEAK is used mostly for studying electron scale physics, right? So we constrain ourselves to have grid spacing and the time step that are electron quantities. For this reason, we are basically with the PEAK we are following the electron dynamics. However, advancement in high performance computing and in algorithmic methods allow us now to study systems that are actually on the ion scale. So the simulation can be ion scale depth along over a large time period. So this is particularly important when we simulate magnetic reconnections. Magnetic reconnection is more a phenomenon related to the ion dynamics that is enabled by the coupling of ion physics and electron physics, and so that's important that we are able to simulate a very long period. So that's why is important to have a more advanced HPC and advanced numerical methods for doing simulation of magnetic reconnection. There are also other tricks, some approximation that we are doing it. We are going to look at this more in the labs. So, for instance, we can assume that the mass ratio between electrons and the protons is reduced. So, in the physical in physics, the real mass ratio is 1,836, right? The ratio between the mass of the ions, of the protons and electrons. So what we can do is actually to assume that the mass ratio is way lower. So it's a fraction of 1,836, and we compress the time scale of and a spatial scale of the electrons and ion scales, right? So keep in mind that the plasma period and other quantities depends on the mass ratio. So by basically changing the mass ratio, we can increase or we can decrease the separation scale between electrons and ion. So this is a very important thing when it comes to magnetic reconnection. Magnetic reconnection is an ion scale phenomenon, so we want to bring all the phenomena related to the ions close to the electrons, so we can actually simulate well with the particle in cell. So these are the governing equations that the particle in cell algorithm solves. So on the top we have the Vlasov equations for two species, electrons and ions. Because this is a plasma, we will always have at least the electrons and the ions, right? So the plasma need to be neutral, so we need two species so that the plasma is neutral. So let's look at how this equation it is. So the main quantity of the Vlasov equations are the distribution function f. So in this case we have Fe, that is for distribution function for the electrons, and Fi, that is the distribution function for the ions. So what is the distribution function? So the distribution function is related to the probability of finding particles at a given velocity and position at a certain time, right? Around dx and dv. So the higher is the distribution in a certain point and certain velocity, the higher is the probability of finding a particles with that velocity and with that particular position. So we have one for the electrons and one for the ions. The distribution function depends on three factors. The first one is the position, the velocity, and the time. So we call this kinetic equation because of the dependency of the distribution function on the velocity, right? So kinesis in Greek is velocity. Because of this dependency, we call this equation kinetic. The other big family of equations that you might heard of is the fluid equations, right? So these are not kinetic equations because the fluid equation, they are equations for the mass, momentum, and energy conservation. If you look at these parameter like the mass and energy and the momentum do not depend on the velocity, right? These just depend on the space. So that's a major difference between kinetic and fluid. So in the kinetic approach, we model what is the evolution of the distribution function. And distribution function depends on the velocity space, right? So this means that we are capable to simulate all the phenomena that critically depends also on the velocity. So what are the phenomena that depends on the velocity? Well, the typical phenomena that depends on velocity, where we need a description over the velocity, are all the phenomena that regards to interaction of a wave particle interaction, So if we have a wave with a certain phase velocity, it will interact only with the particles that have a velocity that is close to the velocity of the wave, like the particle will surf. So if in our model we don't have description of velocity, we're going to miss all these phenomena. So only all those phenomena that depends on a certain population of a particle with a certain velocity, like resonance phenomena, damping phenomena with the waves, we need to have this description. So the particle in cell solve the distribution function equation. They're called the Vlasov equation. So these are called also Vlasov equation because here on the right side we have 0. That means that we don't have collision. So all the if you're using the Vlasov equation, we assume that there are no collision in the system, or that the collision timescale is much larger than all the timescale present in the system, right? So the frequency of collision is actually very low. So our system is developing, but rarely we have a very close encounter to have a Coulombic collision. However, it would be possible to have simulate collisional plasma by adding a term here that is the collisional term. The second piece of the governing equation for the particle in cell are the Maxwell equation that describe the evolution of the magnetic field B and the evolution of the electric field E. So the distribution functions and the Maxwell equation are coupled. What is the coupling? Well, so the coupling is coming from the source in the Maxwell equation. So you see here you see the J, and here you see the rho. These are the charge density and current density. So these are basically related to the distribution function, right? So the J and the rho are the moments or integrals of the distribution function. So the coupling between the first part of this equation, Vlasov equation, and the Maxwell equation comes through the J and the rho that are defined as the moments or the integrals of the distribution function in the velocity space. So the coupling is like integral and differential, so it's a nonlinear coupling that makes very difficult to solve this equation. So what is the particle in cell main idea? So it's very simple. So as I told you, the governing equations is actually the Vlasov equation. That is an equation that gives us the evolution of the distribution function. So the basic idea here is that we start with the initial distribution function that is given as an initial condition, and we represent it as several computational particles. So each particle will represent a piece of this distribution function. So how we do? Well, we assume, for instance, that we have a given initial distribution function, can be a Maxwellian or a Gaussian, and then we sample with the random number generators some particles with a velocity that has a distribution that is this Gaussian. At this point, after we have the sample, we can basically reconstruct the distribution function from our particle distribution. So for instance, we can do histogram binning, right? And we go through all the particles and we divide in categories depending on the velocity, and we go back to the distribution function. So that's the major trick that we do. We start initially from a continuous distribution of our distribution function, and we move to description that is a Monte Carlo-like based on sampling, random sampling of distribution function with computational particles that have distribution, random distribution that is the one that is described. Right. So after we have this representation of our distribution function as particles, we instead of solving the Vlasov equation, we can follow the trajectory of the particles in time. At any time, we can go actually back from the representation of the particles to the representation using distribution function. So this is the most important concept that you need to understand about particle in cell. So we start from distribution functions, so it's a kinetic approach. We sample distribution function randomly with the computational particles, right? So we have like a discrete representation of distribution function using particles. Then we solve the equation of motion, we solve the trajectory of these particles in time. At any time in our simulation, we can go back to the distribution function reconstructed. Right? So the trajectory are calculated by basically solving the Newton equation, assuming that there are two basic forces in the system, the electric field and the Coulombic force, the electric field, and the Lorentz force given by the magnetic field. So here you see that the equation of motion will be a simple definition of velocity of the particle, and then what is the Newton's force, right? So this is basically the mass multiplied by acceleration equal to the forces. So the mass goes to the denominator, and then we have the Coulombic forces, that is E multiplied by Q, and the Lorentz force here in CGS, that is the charge multiplied by the outer product of the particle velocity with the magnetic field acting on the particles. So how many we have? Well, we have as many of these particle trajectory as the many particles that we use in the simulation. So what are peak simulation? Well, peak simulation at the end it becomes, the job is to solve numerically large number of them, each one corresponding to a particle. And then we have a coupling, and then we have a PDE that is related to solving the Maxwell equation on the grid. The coupling between ODEs and PDEs equation are provided by an operation called interpolation, right? So this integral, so this moment calculation is replaced by interpolation step in the discrete world. So we are using discretized equations, so we need to do this basic operation that is called discretization of the time and space. So the time is not continuous anymore, right? But it will be defined only at a certain time level. The same for the space. The space is not continuous anymore, but our variables are only defined in conjunction of certain grid points. So during the discretization of the space, so we go we introduce a grid spacing, a green grid. For the time, we introduce a different time level, so and time step. Right. So we will define, for instance, if we have a quantity defined at the time n on the grid point j, this will be u n and j. So we will have many equations for basically each of these quantity. So it's important point to understand that there are two errors when we do simulation. One of the error is coming from the discretization, and it's called a rounding error. So in this case, we have a discretization error that comes from the fact that we are representing our distribution particle with a bunch of particles. Right, so we are going to introduce some error there. Also we have truncation error. That is when we solve, for instance, the field equation, we introduce a Taylor expansion as a mechanism to derive the equation, and then we stop our Taylor expansion after a certain order. So that will give some error that is given from the numerical scheme. One important point is that all these numerical numerical scheme that we are going to use need to be stable. Stable means that the errors is going to be bounded, so is not growing exponentially. If the error increases exponentially, that means that the error is the scheme is unstable. Right? It might be that we are using certain setup so for instance we choose a time step for which the numerical scheme becomes unstable. So we need to be careful when setting up the parameter of our simulation. Also, it's important to note that quantities that are conserved in real life, so for instance like total energy and total momentum in a closed system is conserved, is not conserved in simulation because of these other error that we are introducing by modeling. So these conservation laws are not satisfied. Some spurious effects might be introduced in simulation. So we might have, for instance, some heating simulations, some collisions that are artificial. The important point is that when we do a simulation, we also check these parameters. So particles in cell are basically part of the big family of particle algorithms. So we use the particle to represent the plasma particles. So electrons are negative particles and ions are positive charge particles. We can use difference in mass between electrons and ions is typically reduced to make the simulation shorter in time. So typical value for the mass ratio is 64 to 156. We typically choose a power of 2 because many quantities depend on the square root of the mass ratio. So that's we get integer number taking power of 2. So what is the effects? So there are several studies as the use of physical mass ratio between electrons and ions. So the major results of all these studies that the major macroscopic details of the simulation, the phenomena do not change. However, very small details at the micro scale, especially when it comes to electrons, might be changing. So how this is representing how the Maxwellian look like? So let's assume. So the major approximation that we do in a particle in cell is to take our distribution function and model with many computational particles. So that's how it looks like. So you see that it does look like a distribution function, but of course we have some numerical affixes that is coming here. So the peak cycle. So any peak code basically is formed in the following way. The first step of the particle in cell method is to initialize the simulation. So what we do is introduce a grid in the system, and we define for each grid point of the grid the electric field and magnetic field. We also do this operation to go from a continuous description of the distribution function to discrete representation using computational particle. So we assume that, for instance, the initial distribution is Maxwellian, and then we sample these Maxwellians with a bunch of particles with a given mass ratio, with a given velocity that is sampled with the distribution function, and with a given space distribution. So for instance, in many cases we assume that the distribution is uniform in space. Right. After this big step of initialization, we complete a cycle, a computation many times. So at each time of this computational time, we updated the different quantities. So for instance, we updated the particle position and velocity, and we also updated the values of the electric field. So we repeat this cycle many times until we simulate all our magnetic reconnection. The cycle consists of 3 major parts. The first one is the particle mover that also comprise a way to calculate the electric field from the grid to the particle position. We have an interpolation step from the particle to the grid, and this is meant to calculate the current and the charge density that are going to be used for the field solver. And finally, we have the update of the electric field and of the magnetic field on the grid. So let's look at the first step. So all the particle methods, and including the particle in cell method, solve the equation of motion that is ordinary differential equation for each particle. Yeah. So for each particle in the system, we're going to solve at each time step this equation here. So this is in the continuous way. The first part is the definition of velocity, and the second one is the Newton's law. So we do this discretization process. So we basically discretize the time in different time slices, and we can come up with a very simple representation of this. So if you have a 2 time step, n plus 1 and n, the first equation can be disguised as this following. So we define a position only at 2 time steps, right? So nothing in the middle. And we can decide that, well, the velocity at time. So this is the way to calculate. We can calculate the position n plus 1 using this velocity here, multiplied by the time step, and then sum it up from this term here. We can do the same trick for the Newton's law here. So we discretize this equation here in this way, and this way here. Right, and then we can reformulate this equation to calculate the velocity of the particle and n plus 1. So this is called the mover, the particle mover, or also called the particle pusher. So when looking at this equation here, we might notice one thing. So we have the electric field and the magnetic field that is acting on the particle. So we need to calculate the electric field and magnetic field at the position of the particle. However, in the particle in cell methods, we have these fields only defined in certain discrete points. So for instance, we can have on the grid points of our cell. So the question is, how do we calculate electric field and magnetic field acting on the particles? How do we calculate the electric field and magnetic field at the particle position? Well, so there are 2 ways to calculate forces. So the first one is basically by brute force. Basically, we calculate what is the contribution by all the other particles, right? So this is called n-body problem. However, this is the complexity of this problem is very high, and is basically a square with the complexity is the square of the number of particles. So this is feasible only for a very small number of particles. If you have 1,000, 10,000 particles, you can stand for this. But if you have more than that, it will take you forever. So this is complexity problem, right? So even if you have a small change in the number of particles, the problem will increase in much larger way, right? So there is not much we can do other than actually formulate a much cleverer algorithm, that is the particle in cell method. So the particle cell method got its name because it's introducing a grid to calculate the forces between particles. So we introduce a grid, and then we define, for instance, at each grid points values of the electric field. So in this case will be Eg. Right? So Eg. And then we will have the particles that is within the cell. So the basic trick that the particle in cell method does is actually to use the values of the electric field defined on the nodes, right? And then make a weighted average and calculate at the position of the particle itself. So if, for instance, if we want to calculate the electric field acting on this particle that is in red here, we can take first we can check where is the particle, right? And then we take all the values of the electric field defined on the nodes. We weighted these electric field values on the nodes by their distance. So if the distance is close, we give more weight. So for instance, we can use a linear weight. And then we sum it up all the different weights to the particle, right? So we make a weighted average. The same here for these green particles, right? So we first check in which cell it is. We take the values of the electric field in the surrounding nodes where the electric fields are defined. And then we take a weighted average of this electric field depending on their distance from the particle. Right? So that's the way we calculate the electric field, but also we calculate the magnetic field at the particle position. So in the particle cell methods, all the electric field and magnetic field are defined only on the nodes. So we need a way to move from the nodes to the particle position. So the next step is actually to calculate the sources for this field solver. So basically there are at least two sources in the governing equation. One is the charge density, right? That it is rho, and one is the current. So here we use a similar trick. So if we want to calculate, for instance, the charge density of the defined on this point here, what we do, we basically check what are the particles that are surrounding this node, and then we deposit a part of the charge to that particular node, right? How much charge we deposit? So we first detect how many particles are in a cell surrounding this node. We take all these particles, right, and then we sum it up part of the charge. So each particle will come with its own charge. It will deposit its charge on this node, right, depending on the distance. Once we have the total charge, we will divide by the volume of the surface. So in this case, it's 2D of the cell, right? So we calculate a density. So this is the opposite flow from the previous operation. In this case, we go from all the particles to the grid point. So we take all the particles surrounding one node in a certain distance, and then we deposit the particle density in a weighted way, depending on the distance, on this point. So we can do this for the rho, for the current density. Also, we can calculate corresponding pressure tensor in this case. The last step of the peak cycle is the field solver, where we solve the Ampere's law and the Faraday's law on the grid. So this is typically done by using finite different technique. So we discretize these two equations and we solve on the grid. We might heard the terms explicit and implicit peak. So the terms explicit and implicit refers to discretization in time of both particle and motion and Maxwell equations. So in explicit peak methods, we use explicit discretization in time. So this is very simple. It's just a simple update. But we might want to use implicit methods that use implicit discretization in time. So implicit peak methods are much more powerful because they are unconditionally stable. That means that the stability of the method does not depend on the choice of the time step, while the explicit methods are conditionally stable. This means that they are stable only with a certain choice of the parameters. So particularly the time step need to be rather small. for having the numerical scheme that is stable. Implicit methods are divided into big categories. One is called full implicit, that solves the couple equation with the nonlinear solver. So in this case, both the equation of motion and the field solver are solved implicitly. Semi-implicitly, decouple the particle of this field PDE by introducing additional equation, making the field solution explicit. So the field equation solution is explicit, while the particle maneuver is implicit. So that's why it's implicit. So it's a part that is explicit and the other one is still implicit. Of course the implicit methods give this unconditional stability, but are much more complicated to solve. So I'm not going to go through, but the PIC code that we're going to use for our lab is using implicit scheme. So we are unconditional stable. But also, if you're going to look at the formulation of the scheme, you will see that is rather complicated. I want to finally go through some parameters that impact in simulation. So in the next lecture, in the next lab, we will ask to set it up some reasonable number for our simulation. And there are some parameters that are extremely important for doing that. So the first question we might have is how many particles we want to set it up, right? Another question we might have is like, which time step I put it there, right? Especially that I know that some scheme might become unstable if the time step is too large. And also, what is the grid spacing, and how I choose depending on the time step can also give some numerical instability. And also, there is another step that not all the PICs have, that is called divergence cleaning. So should we add on, first, what is divergence cleaning? Should we add on or off? So let's look at different parameters that we can set up in particle size simulation. Well, as we saw, to solve the PIC discretized equation is equivalent to solve the discretized Vlasov equation, right? That is our equation for the distribution function plus the Maxwell equation. So the computational particles provide a statistical representation of our distribution function. That also means that more particles leads to have a much better representation of F, right? So and typically the increase of the resolution is scales as the square root of the non-particle. So you have better representation, but not linearly, but with the square root. So the description increase in accuracy, not linearly, but just the square root. So is increased by somehow in a weaker way than the linear, right? So after a certain point, the gain that you can get in using more particles is very much diminished by the fact that accuracy or representation depends on the square root of the number of particles. So why is it important to have many particles? Well, it becomes very important, especially when we want to represent the distribution function on the tail. So that's mean to very high velocity where we have few particles, right? So we might have the tails that are doing some resonance phenomena like Landau damping. If we don't have enough particles, then we might not have this particle represented at a high velocity. And so it's important to have many particles to describe, to have enough particles on the tail of the particles. So the core of our distribution will always have a lot of particles because the probability when we sample will be high in the middle. But the problem is to represent the particle distribution of a function where we don't have particles, right? So one of the problems we might have in particle in cell simulation when we do especially when it comes to simulating damping phenomena, where particle damping kinetic instability is to have enough particles in to describe the population interacting with the waves. So so let's look at an example, right? So here are four distribution functions. So on the x-axis we have the velocity, right? So here in the middle is 0, and then here we have -1 and 1. And then on the y-axis we have, you can see here, we have the number of particles. So this is, we have in the system only 100 particles, and we sample a Maxwellian distribution function. So that's how Maxwellian looks with the 100 particles, right? So it's quite bad. We can do better than that using 1000, and you see, well, that's what we get. So it's still something that it doesn't look like a Maxwellian distribution function. So we also have some problem here that in the tail, as you see, there are probably not enough particles to represent particles interacting with the waves, possible particle simulation, particle species. If you use 1 million, yes, it's increasing from here to here. Sorry, to 10,000. Yes, increasing, but not as much. You see, have many noise, many peaks here, and not very good here also. When we go to 1 million particles, that's then we get somehow reasonable Maxwellian distribution function. So locally, you see that in order to have a pretty decent distribution function representation, we have many of these particles, like 1 million. So the more we have, the better it is, right? This is one of the major disadvantages of a particle insult, that you need to have quite large number of particles to represent appropriately all the phenomena that depends on particles at a given velocity. So the most important parameter when it comes to the stability of the method is the time step. So for explicit peak methods, for numerical stability reason, the explicit peak methods are stable if the time step is less than 1/4 of the plasma period, right? So remember that the plasma period is this basic oscillation to restore charge neutrality. So what we do, we need to sample at least 4 times during this oscillation to have the stability. So this is one of the problems you might have is that the higher the density of the plasma, the plasma period will be shorter. So the time step also will become smaller. So the implicit scheme, like for instance the code we're going to use, allow us to avoid these stability constraints. So implicit scheme are unconditionally stable. So we can have something that is 2-3 plasma period, right? So we don't sample the electric field magnetic field in this oscillation. So the way that is the implicit method works is basically damping electric field components on the frequency of the plasma oscillation, right? So the implicit method does know that it cannot resolve this case. So what it decides is basically ignore it, right, and damp it with basically a filter. That's how works in practice. So we need to keep in mind that plasma period is a local quantity, so we might have different parts of the plasma that have a different plasma frequency. Typical example is magnetic reconnection, where we have the current sheet that is a high density, right? So there in the middle, and then we have it decreases and goes to background density that is quite low. So there is not one plasma period for all the simulation, but each grid point has its own local one. The second important quantities we need to define is the grid spacing. So we need to decide how many grid points and what is how large is the grid space. In explicit peak methods, well, the grid spacing, so the size of the grid, should be less than the Debye length. That is the characteristic screening distance in the plasma. That depends on basically on the temperature, also the thermal velocity, and on the plasma frequency. Implicit methods can also do better than this, because they introduce some kind of numerical damping, and allow us to have grid spacings that are much larger, around 10 Debye lengths. Again, keep in mind that the Debye length depends on the temperature and the plasma frequency. So on the temperature, so is a local quantity. So you might have a part of your system that has different temperatures, so this Debye length also change. It's also is problematic when we have the boundary. So for instance, one of the easiest boundary condition is to put like a perfect conductor, like metallic, so it forms a sheet along the boundary that is typically of the size of the Debye length. So boundary also are problematic when it comes to grid spacing definition. So the last issue I want to talk is that is the divergence cleaning in peak metals. You probably notice when I say that in the field solver we solve two laws. So the first one is the pairs, and the second one is the Faraday. We use these two laws to update the electric field and magnetic field. However, the Maxwell system is an over-determinated system, so there are more equations actually. The reason that we also have the Gauss law, that is the divergence for the electric field, and also the divergence of B equal to 0. So how do we do this? Well, so in peak simulation we also try to satisfy these two other equations, right? So the mechanism we're using is to solve the Ampere's and Faraday's law, but then we correct this electric field and magnetic field by using a correction that is called divergence cleaning. So this divergence cleaning is needed to include also the effects of the Poisson and divergence B equal to 0. So it turns out that in peak metals the divergence of B is always 0 if satisfies at the beginning, but not the divergence of E is equal to rho over epsilon naught. That is the Gauss law. So we need to do something about this. This is called divergence cleaning. So we basically reinforce the Gauss law as an extra equation that is called divergence cleaning. So you will notice in the pre-code that at each time step we do not only solve the Ampere's and Faraday's law, but also we solve a Poisson-like equation that is for doing the divergence cleaning. So the solution of this equation corrects the results obtained by solving just Ampere's and Faraday's law, right? So this is typically important equation to solve because it guarantees the so-called charge conservation, that guarantees that the continuity equation for the charge density is satisfied. So it's strongly recommended that we always have this divergence cleaning, to satisfy these extra equations. So this typically extra equation holds the electrostatic part, also the very high frequency phenomena. So if you want to have highly accuracy simulation, we need to have these divergence cleanings on. So this is my slides. In this lecture, I just want to give you, the basic concepts about peak, the basic concepts about which parameters that we need to set it up. Right? So we look at the basic peak simulation techniques that we're going to use for simulating magnetic reconnection. So in the next lecture, we are going to look at the more practical aspects of the peak, now that you know how the peak is working and what different quantities refer to. So we are going to look at the code to simulate magnetic reconnection. We are going to look at how to provide an input file, and then how to run an experiment for doing magnetic reconnection. Talk to you soon.